So good morning students, this is Arvind, Assistant Professor DBSIT Kavali. So now in this class I am going to discuss some numerical problems on types of DC motors and torque equation of a DC motor. Okay, firstly I will tell the problem data of given problem. So here they given that a 4-pole DC motor is connected to a 500 volts DC supply and takes an armature current of 80 amperes. The resistance of the armature circuit is 0.4 ohms. The armature is wave connected with 522 conductors and useful flux per pole is 0.025 Webers. So determine the speed of the motor. So this is the given problem. So here in this problem they given that number of poles, that is 4, and 500 volts DC supply. This is the input voltage, that is input voltage V is equal to 500 volts, and next they given that armature current, that is IA 80 amperes, and they given that the resistance, that is armature circuit resistance, nothing but armature resistance. So that one is 0.4 ohms, and in this problem they given that it is a wave connected armature. So that means, so you already know this one. So actually we have armature windings, armature winding types. We have wave connection and lap connection. So in the lap connected armature winding we have number of parallel paths is equal to number of poles, but here in this condition they given that wave connected armature, that means here the number of parallel paths is equal to 2, always 2. So that means here I am taking wave connected, that is A is equal to 2, and they given that the number of conductors, that is Z is equal to 522, and also they given that useful flux per pole, that is 5, that is equal to 0.025 Webers. So finally we have to determine the speed of the motor. We have to determine the speed of the motor. So for that one we are using one formula, that is EB is equal to 5PNZ by 60A. EB is equal to 5PNZ by 60A. So here in this one EB is equal to, you know already the back EMF formula of a DC motor, EB is equal to V minus IARA. So in the given problem they given that the input supply is 500 volts. So substitute here 500 minus of IA value, they already given that 80 amperes. Substitute here 80 into armature resistance, that is 0.4. So totally we have the back EMF EB is equal to 468 volts. Okay, this is the back EMF value, and next we have the speed. So from the EMF equation of a DC generator, that is EG is equal to 5 by 60A. Here also I am taking the back EMF formula as 5 by 60A. So by using that formula I am taking that N is equal to EB into 60A by 5PZ. So previously we calculated the value of back EMF, that is 468. So substitute here 468 into 60 into, so here A means that is the number of parallel paths. So it is a wave connected armature, means we have A is equal to 2. So substitute 2 value here divided by flux. They already given that 0.025 Webers into poles. They given that number of poles is 4 and number of conductors is 522, and totally we have the speed 1076 rpm. This is the speed of a given DC motor, speed 1076 rpm. This is the solution for the first problem. And next, coming to the second problem, here they given that a 4-pole DC motor takes an armature current of 6 amperes. So the armature has 480 lap connected conductors. The flux per pole is 20 milliwebers. Calculate the gross torque developed by the motor. So from this one I am taking the first the data. So from the problem, so they given that number of poles, they given that 4-pole DC motor, that means if we have number of poles P is equal to 4, and next armature current they given 6 amperes. 6 amperes, sorry, some problem is there, I am taking that 80 amperes, but here the armature current is 6 amperes. Okay, please change this one. And next we have lap connected armature. So in the previous problem also I discussed this one. So in the previous problem they given that wave connected, that means in that condition I am taking that A is equal to 2, and now in this problem they given that lap connected armature, that means lap connected, that is A is equal to P. That means number of parallel paths is equal to number of poles, and then they given that number of conductors, that is 480, and useful flux, that is 20 milliwebers. Finally, we have to determine the gross torque developed by the motor. Okay, so we have the formula for the gross torque, that is TA is equal to 0.159 into 5 into IA into PZ by A. This is the gross torque formula or armature torque formula also, this one. So here in the problem they given that 0.159 into flux value is 20 milliwebers, that is 20 into 10 to the power of minus 3 into they given that armature current, that is 6 amperes, into the number of poles they given that 4 into total number of conductors, that is 480 by, here it is lap connected connection, means here A is equal to P, that is number of parallel paths is equal to number of poles. So in this problem they given that number of poles P is equal to 4, substitute here, divided by 4. Finally we have 9.158 Newton per meter. Newton meter. Okay, 9.158, that is the gross torque developed by the DC motor for the given problem. Okay. Next, coming to the third problem. So here a DC motor connected to a 460 volt supply has an armature resistance of 0.15 ohms. Okay, calculate the value of back EMF when the armature current is 120 amperes, and next the value of armature current when the back EMF is 447 volts. So here we have to determine the back EMF value in the both in two cases. For one case we have to determine the back EMF when the armature current is 120 amperes, and the next case we have to determine the armature current when the back EMF is 447 volts. Okay, so from the given problem we have to note down the first given data. So from the problem they given that number of poles P is equal to 4. Okay, and next we have armature current, that is IA, they given that 120 amperes, and next we have supply voltage V is equal to 460 volts, 460 volts, and next armature resistance, that is 0.15 ohms. From this one we have to determine the back EMF for the first case, and for the next case we have to determine the armature current IA. So to determine these we have to use the formula V is equal to EB plus IARA. Okay. Next, firstly we have to determine the back EMF value when the armature current is 120 amperes. From the equation V is equal to EB plus IARA. From that one we are writing EB is equal to V minus IARA. So here they given that the supply voltage is 460 minus armature current is 120 amperes into armature resistance is 0.15. Totally we have 460 minus 8, in total we have 442 volts as a back EMF. This is the back EMF value when the armature current is 120, that is 442 volts. And coming to the next one, we have to determine the armature current when the back EMF is 447 volts. So for that one I am writing armature current IARA is equal to V minus EB. So from that equation also I am writing this one, V is equal to EB plus IARA. By using that one I am writing IARA is equal to V minus EB. So in this one we have to calculate the armature current, means I am rewriting this formula as IA is equal to V minus EB by RA. So here they given that the supply voltage is 460 minus back EMF is 447, not 442. This 442 voltage value is for the back EMF when the armature current is 120 amperes only. But here they given that the value of armature current when the back EMF is 447 volts. That's why I am using this 447 volts here. Okay, 460, that is the supply voltage, minus 447 volts by armature resistance 0.15. So finally we have the armature current, that is 86.67 amperes when the back EMF is 447 volts. So this is the solution for the third problem. Okay, next coming to the fourth one. So here they given that a DC motor connected to a 460 volt supply takes an armature current of 120 amperes on full load if the armature circuit has a resistance of 0.25 ohms, and calculate the value of back EMF at this load. So from this problem we have to determine the back EMF value at a particular load. So from this problem I have to note down firstly given data. So from this problem they given that armature current, that is 120 amperes, supply voltage 460 volts, armature resistance 0.25 ohms. So here I have to calculate the back EMF. Here also I am using the same formula for the previous problem also. I am using this one. Here also I am using the same formula. V is equal to EB plus IRA. Okay. And next we have to calculate the back EMF, that is EB is equal to, so from that equation V is equal to EB plus IRA. Here I am writing EB is equal to V minus IRA. So here the supply voltage is 460 minus armature current is 120 and armature resistance is 0.25, and finally we have 430 volts as the back EMF. Okay. And next problem is coming to the fifth problem. So here a 4-pole DC motor takes an armature current of 150 amperes at 440 volts. So if its armature circuit has a resistance of 0.15 ohms, what will be the back EMF at this load? So this problem is similar to the previous one also. So here firstly I will note down the given data. So from this problem I am writing the number of poles P is equal to 4 because they given that a 4-pole DC motor, that's why I am taking number of poles P is equal to 4. And coming to the armature current, so here they given that armature current that is 150 amperes and supply voltage V is equal to 440 volts and armature resistance is 0.15 ohms. Okay, so this is the back, we have to determine the back EMF. So same formula here using for the previous problem also, same formula we are using. V is equal to EB plus IARA, EB plus IARA, and next from this one I am writing EB is equal to V minus IARA. So they given that V is 440 volts minus IA means 150 amperes, RA means 0.15. Substitute here we have the value back EMF, that is 417.5 volts. And coming to the sixth problem. So here a 4-pole 250 volts series motor has a wave connected armature with 1254 conductors. The flux per pole is 22 milliwebers. The motor takes of 50 amperes. Armature and field resistances are 0.2 ohms and 0.2 ohms respectively, and calculate its speed. So from this one we have to calculate the speed of a series motor. Okay, so firstly we have to note down the data from the given problem. So here they given that the number of poles P is equal to 4 and supply voltage V is equal to 250 volts and Z, that is the total number of conductors, 1254 conductors, and flux 22 milliwebers and armature current 50 amperes and armature resistance 0.2 ohms. Okay, and field resistance is 0.2 ohms, and here they given that the wave connected armature, that means here the number of parallel paths A is equal to 2. Okay, so here I am using the formula because here they given that the series motor. Okay, they given that the series motor, that's why from the series motor the voltage equation is V is equal to EB plus IARA plus IARSC. So by using this formula we have to calculate the speed. So if you want to calculate the speed means we have to calculate the firstly back EMF. Okay, so that's why I am taking EB is equal to V minus IA of RA plus RSC. Why? Because from that equation for a DC series motor voltage equation V is equal to EB plus V plus IA into RA plus IA RSC. So I am writing to V minus of IA of RA plus RSC. So from that one I am writing supply voltage is 250 minus armature current is 50 amperes and armature resistance is 0.2 plus series resistance, that is the field resistance also 0.2. Why? Because here the field resistance means here I have to connect the field winding series to the armature winding or DC motor. That's why here the series field winding value is 0.2. So finally we have 230 volts as the back EMF, and next we have speed for a DC series motor. So for that one I am taking the back EMF formula similar to the DC generator. Generated EMF EB is equal to 5PNZ by 60A. So from this equation I am writing N is equal to EB into 60A by 5PZ. So previously I am calculated the back EMF value, that is 230 into 60 into, it is a wave connected armature, that means A is equal to 2. So For that only I am taking the A value as 2 divided by flux value is 22 milliwebers, that is 22 into 10 to the power of minus 3 into poles, number of poles is 4 into total number of conductors is 1254, and finally we have the speed, that is 250 rpm. This is the speed of a DC series motor. Okay, so this is the solution for the problem number 6. And coming to the 7th problem, so in the problem they given that a 20 kilowatts, that is the power, okay, a 20 kilowatts comma 250 volts DC shunt machine has an armature and field resistances of 0.04 ohms and 200 ohms respectively, and calculate the total armature power developed when running as a motor taking 20 kilowatts input. This is the first case. And coming to the second case, as a generator delivering 20 kilowatts as output. Okay, so here we have to calculate the total armature power developed when running as a motor and a generator. For both the cases we have to calculate the total armature power. Okay, so for that one, firstly we have to write the given data. So here they given that power, that is 20 kilowatts, and voltage 250 volts, and armature resistance 0.04 ohms, and shunt field resistance. Why? Because here they given the DC shunt machine. So RSH is equal to 200 ohms. So this is the diagrammatic representation of a DC shunt machine, that means DC shunt motor taking 20 kilowatts input. So in the diagram, here the arrangement is taken as, here I am taking armature winding is parallel with the field winding. So okay, so here the armature resistance value is 0.04 ohms. Okay, next we are taking RSH value as 200 ohms, that is the shunt field resistance. Okay, and supply voltage V is equal to 250 volts. Okay, next, so firstly we have to calculate the line current. Okay, that is line current or load current. IL is equal to P by V. Why? Because in the problem they given that the power. So if you want to calculate the current value, so in the problem they given that the power. Okay, so further for this one I am taking IL is equal to P by V. So here P is the power. So in the given problem they given that power P is equal to 20 kilowatts, that is 20 into 10 to the power of 3 by voltage is 250. Totally we have the line current is 80 amperes. And next we have to calculate the ISH value. Okay, ISH value, the formula to calculate the ISH value, shunt field current value, that is V by RSH. Okay, so here the supply voltage is 250 divided by, they already given that in the problem, shunt field resistance is 200. So totally we have 1.25 amperes as the shunt field current. So if you want to calculate the armature current of a DC shunt machine, we have the formula, that is IA is equal to IL minus ISH. So already we calculated IL value and ISH value, substitute those two values here. So here line current value is 80 minus shunt field current value is 1.25, and finally we have the armature current, that is 78.75 amperes. And finally we have to calculate the back EMF, that is EB is equal to V minus IARA. So here voltage is 250 minus armature current is 78.75 into armature resistance 0.04, and finally we have the back EMF 246.85 volts. And finally we have to calculate the power developed in the armature. This is for the first case. That means the machine is running as a motor. Okay, so here the power developed in the armature formula is EB into IA. So here we calculated both back EMF and armature current previously. Substitute those two values here. Back EMF is 246.85 volts into armature current 78.75 amperes. Finally we have 19.44 kilowatts or 1944 watts. Okay, so this is the solution for the problem number 7. And next coming to the in the first case, for the first case, the problem number 7, first case solution, up to now we discussed it. And coming to the second case, that is the DC machine running as a generator delivering 20 kilowatts output. Okay, this is the connection diagram for a DC shunt generator. So previously I shown that DC motor diagram, DC shunt motor. So here I am showing DC generator diagram, shunt generator diagram. So in this case also I am connecting the shunt field resistance parallel with the generator and armature winding. Okay, so here also we have to calculate the power developed in the armature. Okay, so for that one also we have to calculate first line current or load current. So IL is equal to, we have the formula P by V. Why? Because here they given that the power value. That's why I am taking IL is equal to P by V. So already they given that power value 20 kilowatts. That is 20 into 10 to the power of 3 by voltage is 250. Finally, we have the load current IL or line current IL is equal to 80 amperes. And shunt field current, same formula, ISH is equal to V by RSH. So that is supply voltage is 250 divided by shunt field resistance is 200, and finally we have the shunt field current 1.25, and armature, we have to calculate the armature current. So armature current for a DC series motor is IA is equal to IL plus ISH. So here IL value, load current is 80 amperes plus shunt field current value is 1.25, and finally we have the armature current, that is 81.25 amperes. And back EMF value for a DC generator, back EMF EG is equal to V plus IARA. So here they given that the supply voltage 250 plus armature current, previously we calculated, that is 81.25 into armature resistance value is 0.04, and totally we have the generated EMF, that is 252.25 volts. Okay, next power developed in the armature, that is EG into IA. For a DC motor, that is EB into IA, and for a DC generator, that is EG into IA. So here the generated EMF EG is equal to 252.25 volts into armature current is 81.25, and finally we have the power developed in the armature when running as generator, that is 20.57 kilowatts. Okay, this is the solution for the seventh problem, second case. Okay, and next coming to the eighth problem, that is the back EMF of a shunt motor is 230 volts. Okay, the field resistance is 160 ohms and field current is 1.5 amperes. If the line current is 37 amperes, find the armature resistance. Also find the armature current when the motor is stationary. So from this problem we have to calculate the armature resistance RA value and armature current IA value. So for that one we have to write the given data. So here they given that back EMF EB is equal to 230 volts and shunt field resistance, that is 160 ohms, and field current, that is shunt field current, that is 1.5 amperes, and line current IL is equal to 37 amperes. So if you want to calculate the armature resistance and armature current, we have to use the formula, that is V is equal to EB plus IARA. By using this formula we have to calculate armature resistance and armature current. Okay, so for that one I am taking armature current. So here they given that DC shunt motor. So for a DC shunt motor, armature current IA is equal to IL minus ISH. So in the given problem, they given that line current is 37 amperes minus shunt field current 1.5, and finally we have 35.5 amperes, and supply voltage, that is V is equal to, so you know the formula for the from the Ohm's law, V is equal to IR. So here we have to calculate supply voltage for a DC shunt motor. So supply voltage V is equal to ISH into RSH. So here they given that ISH is 1.5 amperes into RSH value, that is 160 ohms. Substitute here, we have the supply voltage 240 volts. And next back EMF, that is EB is equal to V minus IARA. So for a DC shunt motor, back EMF EB is equal to V minus IARA. So here they given that we have to calculate, they didn't given the supply voltage. Okay, so for that one I am taking back EMF is 230 volts. In the problem they given that the back EMF is 230 volts. Okay, so 230 is equal to supply voltage, that is 240 minus 35.5, that into RA. So totally we have armature resistance value 0.281 ohms. 0.281 ohms. And next armature, we have to calculate the armature current when the motor is stationary. So at this condition, back EMF will be 0. So if the motor is stationary, the back EMF value is 0. So for that one I am writing from the above equation, that is EB is equal to V minus IRA, I is equal to V minus EB by RA, V minus EB by RA. So that is equal to, here the motor is stationary, so at this condition back EMF is 0, that is V minus 0 by RA. So here the supply voltage is 240 minus 0 by RA value is 0.281 ohms. So that is equal to armature current 854.09 amperes. So here one mistake is there, that is back EMF EB. So 230 minus 240 minus 230 is equal to 240 minus 35.5 into RA, that is equal to 0.281 ohms only, not 246.85 volts. This is wrong. Okay. Only we have to take the armature resistance. We have to calculate the armature resistance by using the back EMF value and supply voltage already we calculated, that is 240 volts. So substitute those values here. After that we have to calculate the armature resistance, that is 0.281 ohms. Neglect the 246.85 volts. Neglect that one. Okay. So this is the solution for the 8th problem. And next, coming to the 9th problem. So here the armature of a DC machine has a resistance of 0.1 ohms and is connected to a 230 volts supply. We calculate the back EMF when it is running as a generator, giving 80 amperes, and as a motor taking 80 amperes, giving 80 amperes for a DC generator and taking 80 amperes for a DC motor. Okay, so by using these two conditions we have to calculate the back EMF. Okay, so before going to calculate the back EMF, firstly we have to note down the data from the problem. So from the problem, the data is armature resistance, that is 0.1 ohms, and line voltage V is equal to 230, and find back EMF, that is EB is equal to, we have to calculate the EB. And firstly we have to take the first case, that is as a generator, it is giving 80 amperes. So for a DC generator, induced EMF or generated EMF EG is equal to V plus IRA for a DC machine. Okay, V plus IRA. So here they given that supply voltage is 230 plus armature current 80 amperes into armature resistance, that is 0.1 ohms. Finally we have the EG, that is the induced EMF or generated EMF 238 volts. And next, as a motor, that is it is taking 80 amperes. So for a DC motor, induced EMF EB is equal to V minus IARA. So that is equal to supply voltage is 230 minus IA is 80 into RA is 0.1. Totally we have induced EMF or back EMF for a DC motor is 222 volts. Okay, this is a solution for a solution for a problem number 9. And coming to the last problem, that is problem number 10. So here they given that a 25 kilowatts 250 volts DC shunt generator has armature and field resistances of 0.06 ohms and 100 ohms respectively. Determine the total armature power developed when working as a generator delivering 25 kilowatts as output and as a motor taking 25 kilowatts input. So actually this type of problem I already discussed in the previous problems also. Okay, so same problem repeated here, but the data is different. Okay, but same pattern, same procedure maintaining here also. So here also I am calculating total armature power developed when working as a generator also and a motor also. So before going to calculate these things, firstly we have to note down the data, that is from the given problem, supply voltage V is equal to 250 volts and output power P is equal to 25 kilowatts and armature resistance RA is equal to 0.06 ohms and shunt field resistance is 100 ohms. Okay, firstly we have to take as a generator delivering 25 kilowatts output. So here this is the diagram for this one for a DC generator. So here I am taking the DC shunt generator. That means here the shunt field winding is connected parallel to the armature winding and the DC generator. So this is the diagram for the DC generator. Okay, and next firstly we have to calculate the load current, that is IL. So in the problem they given that the power value, that's why I am taking IL is equal to P by V. So in the problem they given that power P is equal to 25 kilowatts, that is 25 into 10 cube by 250, that is equal to 100 amperes. And shunt field current ISH, we have to calculate the ISH, that is the formula V by RSH. So here the supply voltage is 250 and RSH value is 100. And finally we have the shunt field current ISH is equal to 2.5 amperes. And armature current for a DC shunt generator, armature current IA is equal to IL plus ISH. So that is equal to IL value is 100 amperes plus ISH value is 2.5. and total we have 102.5 amperes. And back EMF or generated EMF for a DC generator EG is equal to V plus IARA. So substitute voltage value 250, that is supply voltage, plus IA value, that is 102.5 amperes, into RA value is 0.06 ohms. They already given. So finally we have the generated EMF EG is equal to 256.15 volts, and power developed in the armature. This is the main thing. So for a DC generator, power developed in the armature P is equal to EG into IA. So here the generated EMF is 256.15 into armature current 102.5, that is equal to 26255.375 watts, that is 26.375 kilowatts. This is the power developed in the armature when running as a generator. And next, coming to the second one, as a motor taking 25 kilowatts input. By using this one, we have to calculate the power developed in the armature. Okay, so here also I am taking the shunt field resistance parallel to the DC motor. So in the previous case I am taking DC generator parallel to the shunt field winding. So here DC motor taking parallel to the shunt field winding. So same repeat. So first we have to calculate the line current, that is P by V. So here the power is 25 kilowatts, that is 25 10 cube by 250, that is equal to 100 amperes. And next shunt field current ISH is equal to V by RSH, that is 2.5 amperes. And for a DC motor, armature current IA is equal to IL minus ISH. Particularly for a DC shunt motor, IA is equal to IL minus ISH. Here the line current is 100 amperes minus shunt field current is 2.5. Total we have 97.5 amperes. And back EMF EB is equal to V minus IARA. So here they given that the supply voltage 250 minus armature current 97.5 into armature resistance 0.06, that is equal to 244.15 volts. And power developed in the armature formula is EB into IA. So for a DC generator, EG into A, that is generated EMF into armature current. And for a DC motor, back EMF into armature current, that is back EMF is 244.15 into armature current 97.5. Total we have 23804.625 watts, that is 23 kilowatts. Okay, this is the solution for the problem number 10. Okay, thank you.